I love coming here. So much of life is about finding your people, and I spent a long time trying to figure out where my people were, and they're here.
Hello, everyone. This talk is about Python bindings. But before we get into that, why am I someone who should be talking about Python bindings for C++? My name is Saksham. I'm a director of quant research technologies at Tower Research Capital. It's a hedge fund based out of New York. We do low latency trading systems in C++ and high throughput data processing and analysis tooling in Python. So that kind of lends itself quite naturally to Python bindings. A little bit more about me. I used to do some program analysis research, some functional programming, well, back in my academic days. Since then, it's just been C++ and Python. I'm pretty happy with those two now. I like performant and clean software APIs. So yeah, Python and C++ have definitely helped in that respect. So yeah, let's get into it. Why are we even talking about Python here? So I particularly like Python, unsurprisingly, because it's like a very simple language. If you have to express a lot of business logic, it's just like really quick to do that. Sometimes you don't want to recompile your entire program just because you messed up one line, so you can like interactively play with this language. It's also very familiar for domain experts in various domains, including machine learning, AI, well, I don't know, lots of different fields at this point. Yeah. Well, someone was happy about the fact that they were mentioned. So yeah, it's an easy-to-use language. There's different tooling, Jupyter, IPython. They make it even more easier for a beginner to use. Like people don't have to learn how to compile a language and so on. It has a lot of open source libraries. So yeah, it's a pretty good language. And why C++? Well, I mean, it's not surprising. We're here. So why do we want to merge them? I guess that's the thesis of this talk. The whole idea being that what if you could, avoid re-implementing complex logic that you've already written in C++. You could keep it very performant, and you could just expose it to your domain experts. You could just make a nice interactive, shell around it, as opposed to like a Unix shell, which has its limitations. Like it can only do a few number of things to whatever you input and output to it. If you manage to expose your C++ program or library with a Python, binding wrapper, it would be pretty cool. Your users would be happy. And there are lots of different ways to do it. There are quite a few libraries. I haven't enumerated all of them here, but there's a few, and we will be talking more about those here. But yeah, that's the rough gist of this talk. Hopefully this talk is going to have some amount of design philosophy, some non-trivial amount of C++, and a very little amount of Python. So without further ado, let's get into it. What are we even talking about? Hello world, but not the usual hello world. I like micro benchmarks. So the hello world I have here for what we're going to be talking about is actually a little different. It's just a simple incrementing function. It takes an integer and returns I plus 1. So the reason I did that is because I can do micro benchmarks on something like that much more easily than I could do with, let's say, something that outputs to std out. We're going to look at a few different implementations of this hello world. For C++, there's not too much to say. I have some code that just runs the increment thing like a bunch of times and gives you the approximate time it took to run that function. Python, it looks pretty much similar. There's not too much extra stuff here. It's just calling that increment function in Python. But here's some new code. This is something called pybind11. It seems to be a library with this like pybind11 module macro. It looks like a macro, right? What we're doing is we're actually saying that there's this m thing, and on this m thing, we're defining a method called increment, which points to this CPP increment function pointer. And there's some documentation for this function. It's called incrementing function, it seems. And well, it turns out we can compile this program into a .so file and load that .so file in Python. And if we do that, we can import this increment function and use that in Python. That's pretty cool. Wow, there's another one of those. There's this other library, Boost Python, which also looks, well, suspiciously similar. There's not any new complexity here. It's the same documentation string and so on. So what happened here? Like, how did we write these .so files, like compiled with C++ and load them in Python? Well, the secret is this guy called CPython. CPython is actually what we know as Python. It's the binary that gets invoked when you write Python on your terminal or you load Python anywhere else. It's the canonical implementation of the Python language, implemented in C, well, for whatever reason. And this is the Python interpreter. It's written in C, which means it actually has hooks to interact with any other C program that you might want to write. What it does is this. It has this thing called a runtime core, whose job is to read in your instructions, your Python statements that you write on your terminal or inside a Python file. It uses them, those instructions, to mutate some internal state. That internal state is represented in this thing called PyObjects. These are just, well, objects in a C land, essentially. These objects maintain all the internal state that your Python has. So if you say I equal 2, there's an object that's pointing to that I variable that you just created. And it has some built-in libraries that let it do like things other than just mutating internal state, like printing to std out or writing to a file or communicating on a network with a socket and so on. So it's got some built-in file libraries that allow it to do that. So what are we doing here? The programs that we wrote earlier, they were definitely not built-in libraries, right? The modules that we created earlier. So what they are actually is a .so file that knows how to interact with these internal states of your interpreter, the CPython interpreter. So the .so file we compiled earlier actually is it's just got instructions that allow it to mutate the PyObjects that are in memory in your CPython interpreter, and that's the gist of it all. So the .so we just compiled, it's called an extension module because it's extending the interpreter's capabilities. The way to do these mutations of these PyObject states is with this Python API. It's a C API. It's in this header called python.h. And it's pretty nicely documented. And all the code we wrote earlier was just some syntactic sugar to actually mutate these internal states, create these Python objects, and mutate them. So yeah, that's what we did. We basically told the interpreter that if someone calls the increment method on this module, what you need to do is you need to call this CPP increment function pointer that we had exposed here. And that's pretty much it. So now the interpreter has been extended. What we really actually wrote is this raw code. And don't worry, you don't have to read it. Hopefully you'll never have to write it. But this is the bare bones way of writing extension modules in Python using the pure python.h API. Boost Python and pybind that we saw earlier were actually syntactic sugars in C++ to just kind of generate similar code like this. There's also this final approach that I want to show here briefly to generate the same code that we have here. It's called this thing called Python. And we'll come back to it later in the talk as well. But this seems to also just do the same amount of thing. If you had your code in a header file, you can actually just bind that code to Python using this language called Python, which looks very similar to Python. And you can also import this in Python and just do the exact same things we were doing earlier. So all of these examples we just saw are equivalent. I have them compiling, and we'll look at how performant they are. But before we go there, I just want to have this slide up for a minute, just to give you an example of all the different kinds of things that people have figured out ways to do with Python and C++ code. The focus of this talk is on this guy. We are probably C++ library authors. We have existing C++ code. And what we want to do is we actually want to make existing C++ code available to our users. There are different, spectrum of software here. Some things are optimized for tuning existing Python code or helping you write new C++ code that interacts with Python. But the focus of this talk is actually on just these three libraries that I have here, Boost Python, PyBind, and Python. So yeah. Well, performance. We wrote a bunch of hello world functions. There were lots of different. They are obviously at least a function call away, all of those hello world increment functions that we wrote. So how fast might they be? Let's see. But given that this is a micro benchmark, we have to take this with a grain of salt. That's just a disclaimer. Here's a grain of salt. So yeah. All right. This is what I have. I've tried it a bunch of times on my PC. It's an i9 PC. And I think the 1000 runs example is like the purest micro benchmark. We have to remember that there's obviously cache effects that are going to show up here. So when you see the 1 nanosecond in C++, that's because everything is in, L1 cache at that point. The increment function is just being called back to back. So yeah, obviously it's going to be very quick. Python is actually not too slow. Each invocation of that increment function in that pure Python program was actually on an average of 67 nanoseconds here. Python C API is 74 nanoseconds, which I would say is just pure noise. It could be 67 itself. PyBind 11 is actually very slow in this benchmark. Boost Python, slightly slower, and Python is actually very fast. So I guess the rest of the talk will actually kind of just develop a mental model of why this is happening this way and so on. But before we move any further, I know there's going to be questions about this as to why PyBind is slower. I did some research, and I found that other people have also noticed that. It's just PyBind 11 has some dynamic memory allocation that it does for every single function call. And that obviously causes this number to not be 74 nanoseconds and so on, because memory allocations are not cheap. But yeah, we can talk more about this later. But these are the numbers that we're dealing with. They're micro benchmarks. But the reason I mentioned them at the start of the talk is because these should guide if Python bindings is a possible solution for your use case. Like if you're not happy with a function call taking 100 nanoseconds extra, then probably not the right approach. But this is just to set the baseline as to what problems we can solve with Python bindings. All right. So let's actually start looking at some design patterns. So the way I've structured this talk is I have a bunch of real-world inspired use cases, and we're going to try to see how to port them over to Python. In my case, I had a custom binary format, and this was a class that knows how to read that format, and it populates some vector of rows, it seems. And we're going to see how to expose this to a Python library, like a Python user, so they can fetch the rows in Python. So this is pre-written C++ code. The equivalent of this, we'll deep dive into this further, would be something similar to this. What we have to do is we have to expose the public API, the user-facing API, to the Python extension modules, well, top level, let's put it that way. And all the internal state can actually just stay where it is. You don't have to mention every single thing. But doing this is the approach we take to providing the API to the user. What happens when we actually try to compile the previous slide is Boost Python ends up generating these to Python and from Python convert functions that get called every time we're actually going between the C++ and Python boundary. So let's say Python has a Python integer, and it needs to be passed to a CPP increment function. So there's going to be a from Python function call in between these two layers. That's going to convert your integer from the Python land to C++ land. And yeah, this is how Boost Python does it. PyBind 11 and Cython will do it differently, but kind of equivalent. So I have a working example of this thing. This is some Python code that imports the module that I just showed you earlier. It enumerates the rows, prints each row's item, works fine. I have some randomly generated data that it prints, mildly inspired by my field of work, but generated with os.random. So there's just some rows with certain key comma value pairs. That's just the example I have here. So with this baseline set, we can actually start developing a thought process about how to structure the Python API that we provide for our libraries. And the first step in that process is that we need to define this thing called a boundary for our libraries API. Everything beyond that boundary has to be, well, hidden in the C++ land. And what we want is all the code that is performance sensitive should be actually hidden behind this boundary. Usually, we'll see exceptions to this. But at the moment, this is a good enough working thought process. Various things, like if you guys know like numpy, pandas, PyTorch, all of these libraries will actually just hide the actual, 10 million long for loop inside the library C++ code. The Python function call will simply be something like compute the mean of these lists and so on. You're not going to do a for loop in Python. So that's the basic thought process. What functions should you expose at this API? A general rule of thumb would just, you init some data structures, you mutate the data structure's internal configuration. You could have functions that do the hard path, which is like, let's say computing the median of like a 10 million long array or something. And finally, fetch some internal state of your data structure. What kind of arguments do we want to have in these functions? Primitive types like int, float, strings, these are reasonably cheap to transfer across the conversion boundary. You could also have vectors. Obviously, it could be more expensive than you might expect. You could also have objects defined by your own module, flowing in and out of your module to and from Python. You could also just have Python objects on the interface boundary. You don't need to have integers. And why would you want to have Python objects in your function? I'll give you an example. The reader class that I had earlier, it takes as input a file name or a list of file names. Python already has like this generic std variant kind of type, which is PyObject, because it can be of any type. There's actually no point of doing the conversion from PyObject to stud variant and then parsing the variant when you could just parse the PyObject. So here I have some code where I just do like check if the list of files is actually a list. If it's a list, then great. If it's not a list, then just assume that it's a single string, and then populate a list of files to open. And yeah, it actually is pretty cheap to do this because this is the bare minimum amount of work you have to do to convert a list of strings to a C++ list of strings. Finally, we have return types, return values. Again, it's reasonable to output primitive types, int, floats, and so on. You can also return Python objects because you know that at the end, like the user is still going to interact with the Python object. So if you wanted to return, let's say, a big JSON dictionary, why not just populate a Python dictionary and let Python layer just use it as it is? The alternative could be, let's say you're outputting a big JSON. The alternative could be you output a string, and then Python parses the string as JSON, but that's just unnecessary conversion cost. You could just populate the Python dictionary in your C++ module if you wanted to. if you don't want to pay the conversion cost. What about larger objects? Should we output large vectors to Python? We can, but usually Python libraries don't like seeing your std vector float and so on. They like seeing some more Python native array types, like numpy arrays. Luckily, there are ways to just populate numpy arrays in C++ as well. So you can just directly populate the numpy array and output that Python object to the Python user. And again, no extra conversion cost. So with this, at least we've covered the input, the API boundary, and the output. We hopefully have a functioning 0.01 mental model of how to define these bindings. So now we can do a full deep dive into the performance and the design considerations behind the library that I was just showing you guys earlier. Just some context on the thing we were looking at. Let's say you have some custom binary format. You have a C++ library that already knows how to parse it. You could write a Python, wrapper around the library that just reads some std out from your C++ library and parses it and presents it to the Python user. But obviously, this is going to be too slow. Also, in general, Python is just too slow with these things. So you could, even if you re-implemented the whole thing, it's not going to be very fast. And you're just re-implementing a library for no reason. So what we can do is we're going to use our Python bindings thing to reuse our existing code, pre-process all the data in memory, not have to go through std out and process boundaries. And we're going to make a DSL so that the user is able to process or do all their usual operations on this data format. We've seen this before. This is the intended user experience with this library. The user should just be able to say, hey, get rows, and they should get the rows. This is, again, the code we've seen before, but the part we're going to focus on is this last line here, because this is the user-facing API here. Of course, you can make it more complicated. You can have alternate get filtered rows, get rows between these two timestamps, and so on. But yeah, this is the user-facing API that we're going to focus on. Again, similar to what we've seen before, let's break down this entire binding code one by one. Firstly, the basics. What we're doing is each row is comprised of a list of items. What we're trying to tell Python here is when I return an item, actually it's a struct with an ID, read-only member, and a value, which is a function that's supposed to return Python object. It's supposed to return a Python object. The reason I'm doing that is value is actually untyped. It could be a Boolean, float, int, whatever. So that's just the API we chose to have. Here's some example I have. Here's the corresponding C++ code and the declaration we were just looking at the bottom. This is just the basics. This is how you tell Python about the member layout of one of your structs. The second thing, object lifetime. Why would we even talk about this? Because Python is a garbage collected language. It has a garbage collector, which means we actually have to think more about object lifetimes than we have to do in C++ in a manner, especially because we're going between a space with garbage collection and a space without garbage collection. So to do that, we're going to focus on this line. So what is this? I'm actually defining this struct called a row ref. It's a reference to a row. It could be anything. In my case, it was a shared pointer to a row object. It has this method called items. This items thing is supposed to return reference, a const auto reference, to an internal stud vector. So do we know what the problem with this thing would be? Returning a reference to an internal member here. The problem is going to be, if you look at this that I have here, let's say you have a function called get first row items, and this function just returns the items from the first row. Once this function has returned, the row object's reference count is going to go to 0, which means that the Python language is going to garbage collect it. So the items const auto pointer that we just got could actually just be dangling. And that's unsafe, obviously. Of course, this can also happen in a C++ API. You could very well make the same mistake in C++, but since this is an unmanaged pointer, we have to find some alternative way to design the same API so we don't actually have these dangling references. So it's an ugly alternative method. So here what I'm doing is, instead of returning a const auto reference to the items vector, I'm actually returning that reference wrapped inside a struct. And that struct actually owns a reference to the parent row. So PyObject star is actually almost like a smart pointer in C++. But since this whole API is for C, the smart pointers have to be manually incremented and decremented, their reference counts. But this is how you would implement something like this. But obviously, this is really ugly. That said, if you return this struct, it's probably going to be safe, because it's going to keep an internal reference to the parent row along with the pointer that you had. We don't want to do this, right? This is too verbose. Luckily, Boost Python has this smart annotation that we can add, return an internal reference, and it actually just does the exact thing we saw, but it does it behind the scenes. What it does is that the returned const auto and ampersand items vector that you returned, it's going to keep a reference to the parent row PyObject inside that Python return value that you returned. So this guy, it's going to return, this items method is going to return a Python object to Python, which has two things in it. The pointer to the items you just returned, and it's going to have a pointer to the parent row object. That's what this return internal does. It's pretty helpful. It allows us to write safe APIs that operate on pointers. Moving on, now we can talk about lists. I have this other line in the binding code where I say that I'm defining that if I return a vector of item, we can call it CPP vector item. That's just for printing purposes. And we're saying that we want to define the semantics of this returned list using this thing called vector indexing suite. Why do we need something special here? Because Python lists operate quite differently from C++ lists, actually. In C++, we are used to having value semantics on vectors. For instance, if you access the first ith element in your vector and you mutate that element, the internal element in the vector is actually not going to be the same because you just made a copy of it. Vectors usually have value semantics. In Python, when people do this, they just expect things to operate like references. So you can think about it this way, that every Python list actually could be treated like a list of shared pointers of the actual object type. So Python users are actually used to that thing. So this vector indexing suite actually wraps around the vector that you return. It changes the methods in that vector to actually do the things that Python users would find more intuitive and natural. So let's try to join these two things we just saw. We saw the vector indexing suite, and we saw the lifetime management of objects. I have this method here, finally, the getRows method that we were looking at. It returns an internal reference to a const auto and of the rows. Will the memory usage increase after doing this? Actually, no, it doesn't, because of all the things we just saw. We're actually just passing on cheap Python objects which have pointers to internal state. We're not making copies at any other place here. OK, constructors. If this looks familiar, I just clicked it 2 hours ago here at the conference venue. But yeah, constructors are simple. We just have to define which argument types this constructor expects and the name of the argument types. Hello? Yeah. Right. So constructors are simple, and there's not too much to say about it, except for the fact that this is a good opportunity to actually talk about two more other things that come up with constructors, at least in this example. That's exceptions and threading. People like throwing exceptions sometimes in constructors, especially when they're not doing two-phase init. Or people like to use threads. Oh, OK. So yeah, exceptions. Exceptions can be set quite easily. Python has this specific way of setting exceptions. Boost Python and PyBind have native handlers to handle C++ exceptions and convert them into Python exceptions. This is just how you do it, but this is usually done by default, so nothing special here. Exceptions are thread local variables, and you can register a handler for your custom exceptions, and those are registered at the interpreter level. You may also have existing code in your library that just aborts or terminates the program if it hits certain error conditions. But if you're compiling a Python module, you probably don't want to make an abort call in the middle of a Python interpreter run, because the user just expects an exception. They don't want their entire process to crash just because some library function terminated. So at least in my code, I just put an ifdef, and I changed all the code that terminates my program to just throwing an exception, and it works pretty seamlessly. Right? We have to remember exceptions are still expensive. There was a talk earlier by Peter at this conference, which was pretty nice, about judicious use of exceptions, and we have to remember those things here. I did some simple profiling. If you throw the same exception over and over using the whole C++ exception stack, then the loop takes around 9 to 10 microseconds on each run, even if you try it 1,000 times, which is really expensive. Python has certain lightweight exceptions that you can look into how to throw, and those are much cheaper. But if you have existing libraries that are throwing exceptions, then, well, you have to live with that 9 to 10 microsecond cost. Of course, these are micro benchmarks, so there are different nuances that can happen in your specific case. Right, and the more interesting topic, threads. So here, I have some simple Python code that what it does is it has 3 files, let's say. It tries to read all those files in parallel. And the exact same code we were running earlier, it's just running that in parallel across, let's say, 3 or 5 or 10 threads. Unfortunately, Python has this thing called a global interpreter lock, which, at least in the short to medium term, we still have to live with. There's some work going on to get rid of it, or make it optional, but not right now. It's a lock that basically has to be taken by any thread that's trying to mutate any internal state in your Python interpreter. It just has to be. Python's internals are not thread safe. But what you can do is, since we were actually just doing simple file I/O and reading the files and maybe processing certain bytes on those files, we actually are not mutating any Python internals when we're just populating the internal memory state. So what we can do is we can actually use these macros, or we can use the RAII construct for that, to discard the GIL in any thread that's trying to read these files, as long as it's just reading the files. We still need the GIL at any other point where we're constructing Python objects or mutating them. But at other times, it's just pretty convenient to do this, and we should definitely remember to use this as much as we can, but safely. The exact benchmark that I had, I was trying to read 3 files. And if you look at the user time, it remains unchanged. But the elapsed time, the wall clock time, is actually 1/3 after I added the GIL, without GIL macro here, the RAII guard. There are different ways to do this. It's just whatever floats your boat. There are certain macros that you can call to do the same thing. All right. So we're done with the first case study. The second case study we have is a more realistic application. Let's say you have an HTTP web server that's trying to serve certain requests. How would we design that? But before we get into it, I just want to define the semantics. I'm going to be using this term called a dispatcher, which just means an infinite while loop that waits on certain sockets and listens to data. And once it has some data, it just dispatches a callback to various listener classes. The way it would look like would be something like this. Maybe you make this new network library, which has a register callback on packet method. So the user can just say, hey, could you call my packet whenever could you call my method whenever there's a packet? And then the Python library has this method called block, which is going to block the Python kernel. And all that's going to happen now after this function is not going to return unless you stop it. It's just actually going to keep spinning and keep calling your print packet function whenever there's a new packet. It has downsides, of course, but this is what we're trying to do. Like, this is the first stage of this thing. This is a very simple dispatcher-based application. Python inits the thing. It registers certain callbacks. To do that, it goes into C++ land so that C++ can save pointers to those functions. And then Python blocks. And now we are permanently in C++ land. You know, C++ may call those Python functions every time it gets a packet, but that's pretty much it. This is very simple. We don't have to think too much about threads and stuff. But we cannot do too much with it. We can't even scale up the workers with this. Why? So if you wanted to have multiple workers, it would end up looking like this. But do we know what's wrong with this? The two threads that we have here cannot actually be mutating and calling those callback handlers without taking a separate lock because of the GIL. At any given time, only one thread can actually operate on Python internals. So what we have to do is this modification to this. We have to release the lock before we actually get into the C++ land and start spinning there. And every time we actually want to come back to Python land, we need to take the lock. So yeah, this is how you would end up designing a multi-threaded, well, server kind of system, which is pretty nice, but can we do some more in this? What if we want to log some information periodically, or we want to monitor some resources? Now the problem is that who has the GIL in this case? Now we have three different running processes, the main Python kernel, and all those two worker processes that I have here. But this is pretty nice. Like, we don't have to do too much about it because if the C++ thing is running in a separate thread, then it doesn't have a GIL as long as it discards it at the time of starting. The Python kernel already has the GIL because that's just your main Python process. It's always going to run with the lock, the global interpreter lock taken by that process. So this is actually pretty nice. Like, now our actual Python layer can just do any sort of simple logic that we want to do. We can add prints into the layer and so on. And the worker processes can just take the GIL whenever there's a packet and do the processing. Works nicely. It'll end up looking like this. And this should work just fine, because whenever Python is going to sleep, it's going to leave the GIL so that the worker processes can take up the GIL and do any packet processing they have to. Finally, there's one extra complexity that we can imagine, is that the Python process actually wants to mutate some internal state that the worker processes are also using. Something like this. In this case, there needs to be some coordination. In this case, we have to do some coordination between the Python process and the internal state. How would you end up doing that? You cannot just mutate state of a different thread on your own. So you're going to have to, well, use certain inter-thread-based locking operations, and you might have different ways of achieving that. In my case, what I do is I keep a separate spinning counter in my worker processes, which waits for instructions from the main Python process as well. But yes, the gist being that it's not safe to just mutate internal state because, again, it's just a multi-threaded program, so that's what we have to live with. All right. Finally, this part, pointers. I'm going to go back to the original program we had with the row reader class. And this time, I'm going to make it more complicated. I'm going to say that the user wants to do their own hot path. They want to write their own for loop over each item, and they want to compute some statistics on it. something like this. So if you look at this code, all of this code is something very specific. It's probably going to be hard to design a DSL for the user in this specific case. They really want to do a for loop on these things. So the user is happy to write code in Cython or Python. They don't want to write code in C++ because, well, it's not a domain. They're not a domain expert in C++. We are. We could provide a pre-built module with all these helper functions like mean, standard deviation, all those statistics that they want to compute. But maybe that's not generic enough. Like maybe the user just wants to do things on their own. Perhaps that's just because we're bad API designers, I guess. Maybe. Maybe the problem is just too generic. Maybe the users actually do want to write the fast loop themselves because they need the configurability and the ease of use of Python. Can't fault them. Do we give up? Let's see. So this is the code we're working with, right? So I'm going to focus on optimizing specific parts of this code. And this is going to illustrate certain very interesting parts about the Python interpreter. So let's focus on these two lines first, the colored lines. What Python interpreter is doing is actually it's going over these lines. Every time it sees these things, it's going to have some bytecode. Like first, whenever you try to run a file, it's going to convert the file into some bytecode. And then it has to interpret the bytecode to actually do the mutations of the internal state that you were trying to get it to do. But what if we could just compile the bytecode into actual C programs? We could, and there's this thing called Python, which just takes a regular Python program, and it converts it to the equivalent C program that calls the same methods that the Python interpreter is calling internally when it sees your bytecode. It takes any Python code, and it converts it into something that a C program can look at. It converts it into a C program, a .so file, an extension module, the same kind of stuff we were doing, but the input here is actually going to be the user's code, not your code. It generates some really hard to read. It generates some really hard to read code. Don't worry, you don't have to read this. But this code is actually going to look, it's actually going to behave exactly like the Python program originally was behaving. Well, a few things here or there, but not semantically, just visually. And it turns out that if we do this on this particular program, the performance does improve. Like I got, well, not too much, but this particular example that I had was 36 seconds, and now it takes 34 seconds. We got somewhere, but the reason I actually took this Python digression is because I really want to optimize this line. Here, what I'm doing is actually I'm calling a function on this Python object called reader. I'm calling a function getIdName on it. What happens when we do that is Python needs to first look up that method object. It needs to find the function pointer that corresponds to the string getIdName. Then it needs to call that function pointer after converting your item.id to a C integer rather than a Python integer. So Python can't do this because Python is not allowed to make assumptions about types of different objects because it is trying to be very consistent with the original Python language's semantics. So what if we could actually get a function pointer to that getIdName, like the C function pointer, the underlying C++ function pointer? If we could get that, like we could just call the function pointer with the reader's pointer, the this pointer of that reader object, and we could get an integer somehow. And this should be much cheaper, right? Because we're not going through the whole like lookup each time. We're not trying to look up the function pointer for that getItemId thing each time. Okay, now that I'm talking too much about pointers, yes, obviously, we're going to get segfaults. That's just a warning, disclaimer. But we have this thing called capsules in Python. They're basically Python object wrappers for pointers. So what you can do is you can actually say that, hey, I have this pointer. I'm going to name this pointer something. And please create a Python object that contains this pointer inside it. It's just a simple Python object. Later on, when you're inside your Python code, you can actually get the raw pointer outside of this Python object. So let's see how that works. This is just some code to generate those function pointers and wrap them in this capsule thing that we just described. But we don't have to look at this too much. It's just boilerplate. But this is the key part of this optimization that I'm talking about. So if you look here, what I'm doing is actually I'm getting these capsule objects, and I'm extracting the pointers out of those objects, the raw C pointers. And since we're in Python land, we can actually use those pointers like C pointers, because Python is just going to convert it to C code or C++ code. And in this case, what I did actually is I got the function pointer for the getIdName function, and I got that outside of the main loop. And inside the loop, I'm just calling the C function pointer each time. We know that C function pointers are cheap to call, maybe 1 to 10 nanoseconds. We know that Python function pointers are expensive to call, as we profiled earlier. That was closer to 100 nanoseconds, as we saw initially in this talk. In this particular example that I had, the runtime actually decreased by roughly 300 nanoseconds per function call. It's not 100 nanoseconds, but I'm going to chalk it up to just cache effects and so on. But it's well within the ballpark of reason. So the disclaimer here is that this was a micro-optimization, and you should only do this if you're trying to expose a very interesting low-level kind of DSL to your user, and you're unable to actually provide them with like a high-level function like numpy.mean or something, where they can just do a simple function call with. This is only useful if they are calling your function repeatedly, which is not always a common operation. Use it as you must, but use it judiciously because this, so yeah. All right, the final section on all of this is some case studies on some open source libraries that also use Python bindings, and we can use them to inspire our own libraries. My favorite is just numpy. It has existed for ages. It's a library to optimize numeric operations in Python over large typed multi-dimensional arrays. It has some simple APIs, like here I have an example. You make a list of 3 integers, and you can call np.mean on it, and it's going to be very fast. Like if the list was 10 million integers, it would still not take the usual amount that Python would take. It's pretty fast. It's actually very widely used in the industry. And the core of this library is actually written in C. Not using Boost Python or PyBind, but what they did is they actually wrote the core with the bare bones Python C API, the one we saw earlier, which, well, if it works for them. The source for the next few slides is actually just their documentation about all of this. But before we get in there, briefly, if we wanted to think about how we would implement a multi-dimensional array library, what we would end up doing is keep some data type in there, keep a pointer to an allocated memory region, keep some information about how big of a memory region you've allocated, how many dimensions it has. Perhaps you'd add some iterator API on this class. So this is what you would do as a C++ library designer, right? What Boost Python was doing for us earlier was actually every time you gave it a class, it was generating some type definition like this, the one we see here. It's actually generating some struct types that have some header, certain, suffix at the end, and your type in between, or a shared pointer to your type in between. So that's what Boost Python and PyBind were doing earlier. With NumPy, the authors actually did not do anything too different. They just took all the stuff we just discussed. They wrapped it in a struct like this. And now this PyArray object struct is now a valid Python struct. You can actually return objects of this type, pointers to objects of this type, to Python from C. And you'll be able to use that in Python and call methods on it. The methods are, kept separately. We don't have to go into the details of it because it's just the business logic of how you implement custom types from C for Python. But what NumPy essentially has is, at the top level, they just have a struct like this. And all their other functions are just operations that operate on a struct like this. Yeah. So what's the takeaway from this? What can we learn from this? They made a core struct, a list struct, and they have found ways to design an API that's actually very useful to people without having to go through the whole pointer kind of stuff that I was showing earlier. You can do mean, median, unique, various other operations based on this struct type that they've defined. And what if we wanted to write some custom hot path and we want to operate over these numpy arrays in our own C++ module? As we saw earlier, we can also just operate. It's just a struct, right? Like we can have C++ API to operate on the struct as well. I have some example code here. I'm just constructing some result vector that I have, and I'm just copying that vector into the numpy array's memory space, and that's it. Like, it's not too complicated. It's just a C array at the end of the day with some extra pointers at the top and bottom of that struct. And yeah. Finally, we have pandas, which is just a more fancier library on top of NumPy. It just uses NumPy, but adds support like enums, timestamps, other Python objects in there. It allows you to slice different multidimensional arrays separately. It allows you to, it's just a higher level DSL on top of NumPy. They actually chose to implement their whole thing in Python. This is just some snippets of some code that I found in their source code. It looks similar to the thing we saw earlier during this talk with Python. Basically, what they ended up doing is they were probably more familiar with Python syntax. So they wrote all their code in Python, but they were able to use the C types and C operations and C for loops because they are just compiling their code with Python. Their benefit is that they get easy interop. The syntax is actually very familiar to most Python users. And they can also import C and C++ constructs that they might have in their header files. Like if you see they're importing the numpy ndarray object.h here. So they can write code that operates on that ndarray type that we just saw earlier. Why aren't we using Python? I don't have a strong argument for or against Python, Boost Python, or PyBind, because they all have different purposes. Python does add a source-gen dependency into your build system, and it's not exactly C++ that you're writing, so maybe some people don't prefer that. But if it works for you, it's a pretty good choice. It's also very performant and a very mature project. All right. To summarize, we can look back at this slide. We found different ways to expose. We've covered 3 of the ways to expose Python users to our C++ libraries internals. And hopefully, we have learned something from this. These are the 3 libraries we saw. And this is basically my grid for choosing between these libraries. I think PyBind 11's documentation is significantly better than Boost Python's, but it has some extra overhead that's not my favorite thing in the world. Python has its own set of problems because it's not native C++, so you have to learn a whole new way of writing things and debugging things. But other than that, it's pretty good. It's very well documented, and it's very fast. Here are some links for all the stuff that I covered in this talk. I have various code snippets locally on my laptop as well. But other than that, I think, thank you. Any questions?
Hi, thanks for the talk. So you have a person writing Python and another person converting it to C++, and the Python continues to get updated, and that needs to get continually ported and updated in the C++.
Sorry, could you repeat that last part?
Yeah, so someone's updating the Python that's been ported to C++. You need to keep the C++ up to date. Is there a way to do that automatically, or do we need to change the entire process so that the Python person is writing Python or something that is convertible automatically already.
I'm not sure I fully understand the question, but when you say keeping C++ up to date, at least my general philosophy has been that C++ is like the source of truth, and then you define a boundary around it that the Python user can always use. So when you say C++ up to date, what do you mean?
It's a direct port of a Python.
A direct port.
Yeah.
Okay. So the hope here is that you don't port, I guess.
Okay.
Yeah. So you probably just keep one canonical implementation in C++, and the Python user just always uses that rather than. So the Python binding code should actually ideally be bundled with the C++ code. That's how I've seen it done in the industry generally. So with that, it's like the C++ person is the one who's responsible for making the corresponding changes to the Python binding as well.
Okay. Yeah. Thank you.
Thanks so much for the talk. I really enjoyed it. When you were looking into the various modules and implementations such as Python and PyBind and Boost Python, did you ever look into NanoBind? My team, we were looking into various wrappers of these, and we ended up picking NanoBind since it was much more lightweight than PyBind. And so I was just wondering if you looked into that at all with your benchmarking.
I've heard that. I think someone told me that NanoBind is just the original author of PyBind deciding that PyBind is too bloated at this point. I haven't looked too hard into it because, well, PyBind, I haven't tried to profile it at least, but Boost Python or Python actually end up working very well for me. That said, if PyBind is any example, then its documentation should also be pretty good. So hopefully, people can pick whichever one works best for them. I'm guessing that it got some fewer features than PyBind 11. That's the original intention for forking, I guess. So yeah, maybe if that limited set of features works for you, then awesome. Yeah.
Thank you.
Yeah.
Thanks for the talk. So I have a question about the social aspect of this PyBind. So if you have a Python library and you have editor support, your users can just jump to the API definition, know what's going on there. But now you have C++ code and you export a .so file. Like, how does your user knows what kind of API is available there, and how do you communicate this with your users?
So I think the only potential solution, the only solution that all these libraries provide here is that you can document various functions in your module. So they can still do the tab complete and they can view the doc string of any function that they're trying to use. But they cannot go any deeper than that. Like if you look at the hello world example, like it had the increment function and there's a string there that says incrementing function. So they can see any documentation string that you write in C++, but there's no way they can jump to the documentation. That's just, there's no good solution that I know for that. That said, in my case, I've just generally kept the code bundled in a fashion that users know where it is. So sometimes they go and read that. But no, it's not a great solution.
Thanks.
Yeah. It's like any other C++ library or program. Like people have to treat that as like an opaque black box, and the help strings are basically the end of the API. Yeah.
Hi. So the Python users, how do they get this library? Do they download the SO file, or do they kind of do pip install and just use it, or how does it work?
For these wrapper binding libraries? So PyBind 11 is actually header-only library.
No, I mean your Python users, when they want to use this.
Yeah, right. So that's a controversial topic. I did not have time for that in this talk, but in general, I have different .so files distributed for different Python environments. So at least where I work, I have a bunch of different Python environments that users use. So I have some build step that every time I commit to these things, it generates a new .so file for each environment. And there's some Python code that I've written that imports the .so from the right place. And it's built with the right versions of pandas and numpy and all those things. It's not an easy problem. I had to, like, the solution I have is not very generic, but it depends on, there are certain other solutions, actually. There's this thing called wheels in Python, where you can distribute these .sos as, like, packages that people can just load, and the packages are kind of tagged by the Python version that they built for, and so on. That's the Python ecosystem way of distributing these .so files. That's how existing things like numpy and all are distributed. Yeah.
Thanks.
Hi. Does any of these libraries provide support for generating type annotations? So mypy or checkpy or any of those linters can read the type annotations from C++?
When you say type annotations, what part are you?
Like in Python, you can annotate that, okay, this function will have a return type, these are the argument types.
Right.
Can you somehow generate that automatically from your C++ code and then make the standard Python linters somehow process that?
It does know that, actually. So whenever you bind any function using those methods, you can actually do a question mark on that function, and it will show you certain string. They're not always readable, but it'll tell you the kind of arguments it's expecting in those functions. If you pass a different argument, it's going to raise an exception saying that I wanted this type, but you actually provided a different type.
Okay, so it will happen at runtime.
Yeah, it has some like introspection just based on, I think they probably implemented it with some CFNA kind of tricks in Boost Python. They just deduce the function signature of your functions and make a docstring out of it.
Okay, thank you.
Yeah. All right. Thank you, everyone. All right.